decoding. Can you see my
Yes, we can.
slide?
Yes, yes.
Is it all right? Or do you need to make it bigger screen?
Yes, it's clear.
Okay, so first we'll try to understand what is actually addressing mode, and then we'll discuss about main 6 addressing mode that we need to understand. There is another one addressing mode, which is the 7th one, the stack addressing mode. We will not cover that one. That's not very important for us as well. So first of all, what is addressing mode? We need to understand whenever we write an instruction in assembly language or in machine instruction, we need to specify our operand. You all understand that one, that whenever we write an instruction, whether it is an assembly language instruction or machine instruction, we need to specify the operand on which the opcode operation will be performed. So every time we write some instruction, we need to specify where is our operand. Now we can specify our operand any one of the 3 places. Our operand can be an immediate constant value, immediate value, we call it immediate value means constant value, or our operand can be one of the register. So register can contain our operand, or the third option is that our operand can be stored in the main memory. So whatever the instruction is, whether it's an add instruction, subtract instruction, multiplication instruction, or division instruction, or any other instruction like shift left logical or shift right logical, add instruction or instruction, so whatever the instruction is, you can see that every instruction you have to specify your operand. That means the data on which the opcode will be performed. So as you know that our instruction, our machine language instruction, as well as our assembly language instruction, any one of this type of instruction, whether it is a machine instruction which is written in binary 101010, or it is a assembly language instruction, our instruction are divided into 2 parts. One is called opcode, another is called operand. You know that opcode is basically which specify the operation that we are going to perform, and operand is basically the data on which we are going to perform the opcode. So our operand can be any one of the 3. As I told you before, that operand can be an immediate value, a constant value, or operand can be a register, where register is containing in one of the operand, or your operand can be the address of the memory location. So just like our variable, when we declare variable, we just use that variable to access the memory location. The same way in your assembly language or machine language instruction, you can specify the address of your operand, that is address which is in the memory location. Yes, who wanted to ask me a question? Anyone wanted to ask me a question? No. Okay. So basically, addressing mode basically tells us that which method we are going to use to specify our operand. Are we going to use immediate value, or are we going to use the register to specify our operand, or are we going to use the address of the memory location to specify our operand? So this addressing mode basically tells us that in which way we are specifying our operand, either using the immediate value, or using the register, or using the memory location. So they have different variation. Definitely, we will see that all these operand can be specified either as an immediate value, or as a register, or as a memory location. How we can implement that? That we will see that in any one of the 6 addressing mode. Now remember, every computer architecture, they either use two or three of the six addressing mode. I don't think so any one of the architecture they use all the six addressing mode, but most of the architecture basically use at least three or four. Uh, Three or four addressing modes are used by most of the architecture. So we need to understand what are those addressing mode. And as I told you, addressing mode is nothing but how to specify your operand in your instruction. How to specify your operand in your instruction. Now, addressing mode basically tells, for example, we have one addressing mode which is called immediate addressing mode. So this immediate addressing mode, basically the name itself is stating that in this addressing mode, the operand can be specified by the constant value. So this is very simple addressing mode, and in that way we have another addressing mode called direct addressing mode. We have an indirect addressing mode. We have a register addressing mode. We have a register indirect addressing mode, and we have a displacement. So these are the six addressing modes we are going to actually dig, and we'll try to understand each of them. But as I told you, the addressing mode basically tells us that how the operand will be specified in your instruction. So every instruction, whether it is a machine instruction or assembly language instruction, we need to specify our operand. For example, you can remember that we usually write this kind of instruction. For example, add I. Can you see that? Can you see that?
We see just the
Yes, Dr.
first part. Yes, now I see.
Okay, so add I dollar, say for example T0 dollar T1 comma dollar zero, sorry, dollar 15, value 15. So this is an instruction. You can see that this is also an instruction, and this instruction you can see in this instruction, one of the operand is a constant value, the immediate value. The other operands are registered. So any kind of instruction, you'll see that some operands are being used, the immediate value being used to specify the operand of that for that instruction, and some cases you can see the registers are being used to specify the operand of the instruction. So here you can see that we have some operand. One of the operand is immediate value, another operand is register value. So first addressing mode that we are going to explore, which is called immediate addressing mode. In case of immediate addressing mode, the operand will be specified by the immediate value, the constant value. This is the most easiest addressing mode, where you can see that the one of the operand will be the constant value. One of the operand will be the constant value. So in case of immediate addressing mode, this is the simplest one. So as I told you that most of the computer architecture either use three or four of these addressing modes. Not all of them, but at least three or four addressing modes are used by the most of the architecture. So the first addressing mode is immediate addressing mode. In case of immediate addressing mode, you can see that in the instruction, this is your opcode and the remaining is your operand. Now one of the operand will be your immediate value. Now the question is that in your instruction, definitely this is the simplest addressing mode, where you can see the one of the operand will be specified by the constant value, that is immediate value. So this is the simplest addressing mode. But the question is that what is the size of your instruction? If your instruction is, say for example, 16 bits, again, if your instruction is 16 bits, how many bits will be used for the opcode, and how many bits will be used for your operand, especially the immediate operand that we are talking about. So if you have only 16-bit instruction, and if you need to specify only one operand, for example, in case of li instruction, say for example li instruction, li instruction dollar d0, sorry, dollar d0 comma 5, comma 5, you can see that one of the operand is a constant value, another operand is a register. In case of immediate addressing, the question is that how many bits will be used for our opcode. For example, load immediate is the opcode, and how many bits will be used for the destination register, and how many bits will be used for your immediate value, constant value. So if you have only 16 bit, and out of that 16 bit, if I use say 5 bits for the opcode, then we have 11 bits, and out of 11 bits, we can use 4 bits for the our destination register, 4 bits for the destination register, and remaining 6 bits you can use for the immediate value. Now, when you are using only 6 bits for your immediate value, you can able to understand your constant value cannot be very big. Are you understanding, boys?
Yes, clear.
Everyone? Again, if your instruction, say for example, you make a instruction table. Okay. Now, if this is your total instruction, and if your opcode, this is your opcode, and if opcode requires, say, for example, we are taking 4 bits for the opcodes or 5 bits for the opcodes, then you see that this opcode, Li, is our opcode. We can use 5 bits because your total instruction, for example, the size of your total instruction is 16 bits. And out of these 16 bits, if we use only 5 bits for the opcodes, then using 5 bits, you can have 2 to the power 5, that is 32 different opcodes you can have. And if we take our destination register, you can see that our destination register, if we take 4 bits for the destination register, then you can see that 4 plus 9 is already 4 plus 5 is 9, already been used for this part. Then remaining constant value, if you want to immediate value, if you use remaining 7 bits, now using 7 bits, what can be your maximum value? Who can tell me? If you have only 7 bits for your immediate value, what can be your maximum value?
2 power
16.
7.
To the power 7.
To the power 7, which is equivalent to 128 unsigned number, 128 unsigned number, I think. But if it is a signed number, that means 2's complement representation, it can be minus 64 to plus 63. Only minus 64 to plus 63. You can able to understand that with that 7-bit only, you cannot use a huge big number. So, fortunately, our instruction size is not only 16 bits. Usually, most of the time, instruction, especially in MIPS, instructions are 32 bits. And since it is 32 bits, you can use again 5 bits for the opcodes. Registers, you can use 5 or 6 bits. So for example, 5 bits. And in that case, in this particular case, you can use immediate value. For example, remaining 22 bits you can use for the immediate value. Then you can have a huge big number. But most of the time, what happens that anyone any question? No. Okay. Most of the time, what happens that we need to use some other register. So we need to spend some bits for the other register as well, another source register as well. So for example, ADI instruction, if you see the ADI instruction, in case of ADI instruction, there is one register for destination, one register for one of the source operand, and one is your immediate addressing value. So if we take these 5 bits for the opcode, the first destination register is 5 bits, and first source register is also 5 bits. So 15 bits will be gone, or 16 bits will be gone, and then the immediate value will get only 16 bit. With 16 bit again, I think you can have maximum 32,768. So that is not a big number. So this is one of the limitation of immediate addressing, though it is the simplest addressing mode. But one of the limitation of this addressing mode is that you cannot have a big number. So, but definitely the immediate addressing mode main advantage is that it's a simple one because you don't need to refer to any memory location. And since you don't need to refer to any memory location, you can get your value from the constant value, from the immediate value. So since no memory reference is required, so what will happen, you don't need to spend the time for reading the data from the memory or storing the data from memory. As you know that reading or writing data from memory or into memory requires good amount of time. So in case of immediate addressing, we are not referring to the memory. Our operand are not in the memory, so it will be faster. That is the advantage. A disadvantage is that your immediate operand size or range of your immediate value cannot be big because we cannot spend a lot of bits for the immediate value, and that is the disadvantage, that your numbers range of the number cannot be huge. It is limited, restricted because of the number of bits. You cannot use a lot of bits for the immediate addressing. So the second addressing mode is called direct addressing, and this direct addressing actually used to be used a long time before, 50, 60 years back, when we used to have a very small memory. At that time, direct addressing was very appropriate, but nowadays direct addressing is not at all appropriate, because in case of direct addressing, what happens, your instruction itself will contain the address of the memory location. Your instruction itself will contain the address of the memory location. In fact, in MIPS, we don't have any kind of instruction like that. But previously, as I told you, 50, 60 years back, when they used to write the add instruction, they used to say 2568, which is basically memory location, and comma, then 3678 memory location, then comma 2589. So these are what the instruction where you specify the address of the memory location in your instruction, address of memory location directly. So that's why this is called direct addressing, where you specify the address of the memory location directly. But nowadays we don't use the address of the memory location directly. The main reason is that if we put the address of the memory location, we cannot use too many bits. For example, even if we have a 32 bits for direct addressing, try to understand we are now in the direct addressing. In case of direct addressing, what you can specify in instruction, other than the opcode, all your operand and destination operand, all can be specified by the direct address of the memory location. By the direct address of the memory location, you can specify the direct address of the memory location. Now, if say for example you have one of the operand which is specifying direct address of the memory location, it can be like this as well. It's not necessarily that all the operand will be the direct address. It can be also like this. For example, your P0, 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 then T1, T1, and the direct address is this. That means what will happen, one of the operand is in memory location. Even one of the operand is memory location, you can see that this memory location data, the value of this memory location will be added with T1, and finally the result will be stored in T0. In this case as well, though this kind of instruction is not valid nowadays in MIPS, it was previously 50, 60 years back, it was possible that you can specify the address of your memory location directly in your instruction. But nowadays, we cannot specify the address of the memory location directly in our instruction. The main reason is that nowadays our memory is huge, big one. We cannot specify the address of the memory location in your instruction, because the address of the memory location nowadays will be 32 bit or more than that. And you cannot spend 32 bits for the address of one of the memory operand of your instruction, because your whole instruction is 32 bit. How can you specify the address of a memory location which is also 32 bit? Are you following my problem?
Yes, clear.
So in case of direct addressing, try to understand direct addressing nowadays it is not being used. It was used to be used long time before, 50, 60 years back, when the size of the memory was very small. Maybe say, you can say 1 kilobyte of memory, main memory, 1 kilobyte of main memory. You know that 1 kilobyte of main memory means 1024 bytes. If you have a 1024 bytes of main memory, then it is possible that 1024 bytes of main memory you can refer using, I think, 10 bits, using 10 bits. So even for 1 kilobytes of main memory, if you want to refer to each byte of your main memory, you need minimum 10 bits. Now, if you spend 10 bits for only the address of the memory location, then what will be your other bits? So you need some bits for your register, some bits for the opcode, so all those things. And that's the reason actually direct addressing nowadays not being used. And the main reason of direct addressing is that main disadvantage of direct addressing is that you cannot refer to a higher memory location, or the address of the memory location which is bigger cannot be used in the direct addressing. So that's the reason in case of direct addressing, the size of your memory will be very small, very small. And that was when the situation 50, 60 years back, only maybe 1 kilobyte or maybe 8 kilobytes of memory you can able to access using direct addressing mode. Remember, direct addressing mode, you can see here that this is your opcode. Can you see the picture?
Yes, we see.
Yes, Doctor.
This
Yes.
is your opcode. Opcode can take small number of bits, maybe 5 bits, 6 bits, and remaining bits can be used for the address of the memory location. Now, if your instruction is only 16 bits, 5 bits or 6 bits if you use for the opcode, then remaining 10 bits you can use for the address of the memory location. Now, 10 bits address of the memory location means your size of your main memory can be maximum 1 kilobyte, only 1 kilobyte. But nowadays we have gigabytes of memory. So direct addressing nowadays is not possible. Is it clear to everyone?
Doctor,
Yes.
can you speak about the effective address? I think it's like this.
Okay. Okay. Effective address. Whenever we are talking about register, main memory, or our immediate value, that's our effective address. But remember one thing: this effective address is going to be converted to physical address by the memory management unit. So memory management unit basically convert your effective address to physical address. Now, for us as a programmer or as a student of computer science, we'll always refer to effective address. That means whenever we are saying this is the one of the operand is in your register, when we are saying register, that is our effective address. When we say that this is the address of the memory location, that is our effective address. But actual effective address or actual address, physical address, will be converted from the effective address to the physical address by the MMU. So for a programmer, we don't need to be worried about the physical address now. We just need to be worried about the effective address. And whatever the address we are talking about here, these are all effective address. They are not the physical address, because physical address will be converted from the effective address, or effective address will be converted to physical address by the MMU, which is a small device, hardware device in your computer. So MMU converts our effective address to physical address. So whenever we say this is a immediate value, that's our effective address or effective address for the operand. This is our register, which is containing one of our operand. That's our effective address. This is our memory location that is containing one of our operand. That's our effective address. But their actual physical address will be calculated by the MMU, memory management unit. So is it clear?
Yes, yes.
Okay. So here, whenever you say effective address, that's our address. That's the address of our data. It can be register or it can be memory location. So whenever we are talking about the effective address, but it will be automatically converted to the physical address by the memory management unit. When you go to the operating system, you will understand this difference between the effective address and physical address very well. But now on, you don't need to be worried about that one. because that's actually out of our context. Anyway, so after finishing the direct addressing, you can understand direct addressing mode are not being used nowadays, especially when you have a huge amount of main memory. When your memory is size is very big, it is not possible to refer to one of the memory location, memory byte in your instruction, because in your instruction itself is 32 bit. Out of 32 bit, you cannot use all 32 bit for referring to one of your operand which are in the main memory, because nowadays our main memory is so big, our address for one byte is 32 bit, but your instruction is also total 32 bit. So how can you refer to a memory location which is containing one of your operand and that memory location address is 32 bit? You cannot specify that in your instruction. So that's why nowadays there is no direct addressing. We always use indirect addressing. Now, what is indirect addressing? In case of indirect addressing, what we do, uh, we contain some memory location definitely, but the range of that memory location is within 1 kilobyte to 8 kilobyte, like that, because you cannot spend a lot of bits for your memory location. So in case of direct addressing, what we do, we specify some bits in our instruction so that we can refer it to lower part of the main memory whose address is not that big, whose address is can be referenced, whose address can be referenced using say 10 bits or 12 bits. So lower part of the main memory can be referenced from your instruction, and that lower part of the main memory will contain the actual address of your operand, actual address of your operand, while your actual address of the operand is 32 bit. So this memory location will contain that 32 bit, which is basically containing the real your operand. Again, indirect addressing is just like in your instruction, you will refer to some memory location which are not your real memory location, because this memory location are only in the lower part of your main memory, because you know that main memory starts from 0000, then maybe 0001, then 0002. These are the memory location you can refer using say 8 bit or 10 bits or 12 bits. That is enough. That is more than enough for an instruction to refer to those memory location. Those memory location can be referred using 10 bits or 12 bits, because you have to always remember there is a restriction in your instruction. Your instruction cannot be more than 32 bits. So if you want to refer to a memory location whose address is 32 bit, it is not possible. It's not possible that you can refer to those memory location. So you can refer only those memory location whose address is can be referenced using 10 bits or 12 bits. So in case of indirect addressing, what we do, we refer to those memory location that can be addressed using 10 or 12 bits. So in that case, we go to a lower part of the main memory, because these are the starting address. Their address is small, and these addresses, so they are referring to this memory location, and this memory location will refer to actual memory location where is your operand is. Are you following what I'm saying? Can you difference the direct addressing and indirect addressing?
Direct maybe refers to the whole memory, and indirect it refers to a specific size or limit range in the memory.
Okay, okay. It's almost okay, but I'm not sure whether you can visualize it. So what I can do, let's Try to understand, if you have a huge big memory, the initial memories maybe address is like this. Like this. But as you grow, you will see that your address will start like this. Like this, where you need all 16 bits to refer to this memory location. But here you just need last 4 bit to refer to this memory location, or if you need last 8 bit to refer to this memory location. But here you need all 16 bit to refer to this memory location. So that's exactly what I'm trying to in direct addressing. In direct addressing, because we have one limitation of all kind of addressing mode, that our instruction size is 32 bit. So within that 32 bit, you cannot spend lot of bits only for referring to a address of the memory location. You can spend some bits for the opcode, you can spend some bits for your other register, and you spend some bits for referring to the address of the memory location. Now, if you need to spend all 16 bits for referring to the address of one memory location, what about your other operand? So you cannot do that, but you can refer to this memory location where you need only 8 bits. This memory location you just need 8 bits, because the remaining bits are 0, so you don't need to be worried about that. So this memory location you can easily refer using 8 bits. That is exactly what we are doing in indirect addressing. We spend only 8 to 10 bits for referring to the lower part of the memory, which can be referred with 8 bits or 10 bits, and they will basically contain the actual address that you want to access. For example, actual address that you want to access, which are 32 bit maybe. So these are containing 32 bit. So you can see these are 32 bits, but these 32 bits we cannot refer. These 32 bits referring to the memory location which are higher in the main memory, and those memory location cannot be referenced in our instruction, because our instruction itself is only 32 bits. It can refer to one of the operand using 8 to 10 bits, and using 8 to 10 bits it can only refer to smaller memory location where their addresses are smaller in bits. So we can use those addresses, and these addresses of the memory location is containing your real address, higher address of the memory location, which is containing your actual operand. So in case of indirect addressing, try to understand that they always refer to lower part of your main memory that whose address is smaller in size, so that from that address you will get the actual address of your main memory, and that actual address of the main memory is containing your operand. Remember, this address which is given in your instruction is just containing the address of a memory location, where the address of this memory location is containing real address of the memory location, not real, we should not say real, the actual size of the memory location, address of the memory location that is containing your operand. Are you understanding?
Yes, clear.
So that's a indirect addressing. Then the other one is register addressing. This is a much easier one because our instruction can refer to a register. So definitely our instruction can refer to a register. You can see that this is our one of the instruction. You can see, sorry, you can see our instructions usually refer to some of the register. So register addressing is basically another addressing mode where instruction contains the number of the register, and that register contains your operand. So instruction does not contain the operand, rather its instruction contain the number of register, which number because you know that like MIPS, we have 32 register. Every register has a different number, though we call them by their name, V0, A0, T0, S0, but they all have a name. Starting from they all have a number, starting from number 0 to number 31. So every register has their number. So in case of register addressing, in the instruction, we don't give the register name actually, rather we provide a the number of the register where the register contains your. Are you following what I'm saying? Boys, this is your chance to ask me a question. Any instruction, if we provide any instruction, the instruction itself will not contain your operand. Rather, instruction will say that which register is containing the operand. So what it will do in the instruction, it will specify the opcode, and then it will specify the register number that is containing your first operand or your destination operand. Then it will provide the register number which is containing your second destination operand, and then it will contain it specify the third register or your second source register, the register number which is specifying the third or second source register. So in case of register addressing, for example, if we go to this kind of instruction where you can see $T3. So what is happening? You can see the three registers, all are registered. So register addressings are used completely in MIPS as well. So you can see that all registers are specified. So if we see the corresponding machine instruction of this, if we see the corresponding machine instruction of this, and if we remember that machine instruction can be 16 bits or 32 bits. If it is 16 bits, we can use say 5 bits for the 5 bits for the opcode, or 4 bits for the opcodes. So 4 bits for the opcode, we can use 4 bits for the opcode. First destination register, we can also take 4 bits. Then we can use we can use the first source register, we can also take 4 bits, and second source register, we can also take 4 bits. Now what will happen if we have say add has a opcode 1101. This is our opcode add. Destination register number T0. T0 is, for example, number 16. With 4 bit, we cannot represent number 16. So T0 is register number 5 or 6. So that 0101 register number 5. First source register can be register number 4, and second source register can be register number 3 or 7. Say for example, I think 9 can be. So 1001. So you can see that this is a one simple instruction, machine instruction, where the first 4 bit representing your add, second 4 bit representing one of your register, destination register. This 4 bit is basically telling which register is containing our first source register value, and this number is basically telling which register is containing our second operand. So the first operand is in the register number 4, second operand is register number 9, and the result will be stored in register number 5. So this is one example how register addressing can be used. So remember one thing, when you have a 4 bits, that means number of register you can refer in your instruction. Number of register you can refer in your instruction is 2 to the power 4, which is 16 register you can have. So in this case, your machine instruction size is 16 bits, and your one of that register can be 16 register, because you have only 4 bits for referring to one of the register. Are you following? That's a register addressing. And
Sir, can you repeat again?
yes. Now, register addressing is very simple. Register addressing, basically we specify the register which is containing our operand. Now, how we are going to specify our register? We can specify the number. So that is exactly what I say, that in your register addressing, if this is your register addressing, this is a complete register addressing, because all your operand in your register, all your operand in the register.
Doctor,
So
the
that's
video is stopping. It's not.
no videos.
No, it's a freeze. The
It's
vector is
frozen.
freeze.
Can you see it now?
For me, it's okay.
Okay, I will refresh and relog in.
What about the others?
No, it's working, doctor.
It's working for me.
Okay. Okay. So register addressing, when we say a register addressing, means in your instruction you have to specify which register is containing your operand. In your instruction you have to specify which register is containing your operand. So in your machine instruction you can specify T0, T1. In your machine instruction you have to specify the register number. So if it is a machine instruction of 16-bit machine instruction, say for example you have a machine instruction of 16 bits, so what will happen, you can see that we can use 4 bits for our destination register, 4 bit for our first source register, this is our first source register, and 4 bits for our second source register. So for the machine instruction, basically you cannot specify the register number, the register which is containing one of the operand. You cannot say T1 is containing one of the operand, T3 is containing one of my operand, and T0 should be my result should be stored. Because in machine instruction you have to specify all with 0 and 1. So what we do for say T3, which is say for example it's the register number 9, so we'll put 9 here because T3 is basically represented by 9. So T1, maybe this is the register number 4, so we'll put number 4 here. That is telling that register number 4, which is T1, is basically containing our first source register, and register number 9, which is a T3, which is containing our second source register. And our result will be stored, add operation result will be stored in the destination register, and that register is 0101. So that is the register number 5. So in register addressing, we usually refer to the operand by using the register. So in our machine instruction, usually we don't specify the register name, rather we specify the register number. So register addressing is very simple,
Doctor.
because here, yes.
And all of them are sharing the 16 register, or each one of them have 16 register?
Here you are talking about this one?
Yes, yes.
So destination register can be one of the 16 register, source register can be one of the 16
Okay.
register, and second source register can be one of the 16 register. Which 16 register, you have to specify their name, number. Are you understanding? Which register you are using, you have to
Yes,
specify
yes.
your number in your machine instruction. Okay, so register addressing is much easier, but there is another one is called register indirect addressing. In case of register indirect addressing, what we do, this is register indirect addressing is just like our indirect addressing for memory location, but in case of register indirect addressing, what we do, the register contains the address of the memory location, and we go to that address, and then finally from the register we get the address of the actual memory location. So try to understand, in your instruction will specify only the register number that is containing your operand. Actually the register is not containing in operand because it's a register indirect. When it is register addressing, in your instruction we specify the register number, and register is containing your operand, which is register addressing. But in case of register indirect addressing, your instruction will contain the register number, so you go to that register you will find actual memory location of your operand. So operand is basically stored in memory location, but their address is stored in the register, and in the instruction we are referring to the register. So in order to refer to a register, you need only 4 bits or 5 bits, but refer to a memory location, you need 16 bit or 32 bit. So that's the reason we use register indirect addressing, and in fact register indirect addressing are being used nowadays, and in our NIPS also we use register indirect addressing. When you go to the array accessing, you will see that we are using register indirect addressing. So in case of register indirect addressing, what we do in the instruction, we don't contain the address of the memory location. Rather, in the instruction, we contain the number of the register. And so we'll say that my operand is stored in the register number 5. So you have to go to the register number 5. These are all you register. You will have to go to the register number 5. But register number 5 is containing the address of your actual memory location that is containing your operand. Are you following what I'm saying?
Yes, clear.
Yes.
Okay. So register addressing and register indirect addressing, try to understand the difference. Register addressing, the instruction contains the number of the register, and the register is containing your operand. But in case of register indirect addressing, instruction is containing the number of register, but register is not containing your operand. Register is containing the address of your memory location, where the memory location is containing your operand. So that's why it's called register indirect addressing. Are you understanding? Boys.
Yes, clear.
Okay. Now, displacement addressing. In case of displacement addressing, you will see that it's a very powerful mode of addressing, displacement addressing. But out of this displacement addressing, there are mainly 3 different type of addressing we'll see. One is called relative addressing, and this is called base register addressing, and that is called indexing. Now, in case of displacement, what happens actually, relative addressing, what we do in case of relative addressing, this addressing we use for accessing instruction from the main memory. So what we do, as we know that accessing instruction from the memory, we need the program counter register. Program counter means PC register, and PC register contains the current address that CPU is going to execute. But with the PC, we add some displacement so that the CPU can jump to a particular instruction where it is supposed to execute. For example, sometimes we are executing if statement, and if statement or for statement jumps from exit. For loop jumps from the exit. So you have to jump from the current instruction, you have to jump, say, 20 bytes away where your exit instruction is there. So relative addressing, basically, we need to work with a program counter register. With program counter register, we add some displacement that where is our next instruction. So it can be 4 byte away, it can be 8 byte away, it can be 12 byte away, it can be 16 byte away, it can be 100 byte away. But that 100 byte will be added to our current value of the PC program counter register, so that we can go to the appropriate instruction where the next instruction is going to be executed by the CPU. So relative addressing, you don't need to be worried about that much. And I am not also very much worried about the relative addressing, but I am more interested about the base register addressing and indexing. Now, relative addressing, I'm just finishing relative addressing. Remember, relative addressing is used for accessing your instructions. CPU usually access instruction which is pointed by program counter. But sometimes, you know, the for loop or if statement, we need to jump from our current instruction to a instruction which is further down, say 100 byte away, 200 byte away, or 300 byte away. So if we want to get the address of that instruction, what you have to do, you have to add the displacement, the 100 bytes or 200 bytes away, that is your displacement, need to be added with the current value of PC, so that CPU can go to the exact location where is the next instruction is there. So CPU can execute that instruction. So that is called relative addressing. Relative addressing is only for accessing the instruction, and we need to use the PC program counter register to access a particular instruction which is away from the current instruction that CPU is executing, away from 100 bytes or 200 bytes or 300 bytes, and that 100 or 200 or 250 bytes are called displacement. So this displacement basically help us to get the actual address that CPU needs to execute. But base register addressing and indexing are used for accessing your data. Base register addressing and indexing basically used for accessing your data. Now, in case of base register addressing, what we do, we use one register and one displacement. Now, registers usually we for base register addressing, the interpretation is following. The reference register contains a main memory address, and the address field contains a displacement. So in your instruction itself, you will have two parts. One part will contain the number of the register that is containing the main memory address, but that main memory does not contain your operand. So with that address, you have to add some displacement, and that displacement is also in your instruction. Try to understand. This is not your register indirect addressing. In case of register indirect addressing, what happens in the instruction, we give the number of the register, and we go to that register. In that register, we create the address of the memory location, and that memory location contains the operand. But here, in case of base register addressing, your instruction contains the number of your register, where register contains the address of the starting address of some memory location, some block of memory location. We call it segment. Starting address of some block of memory location, and your instruction also contains some displacement. So what you have to do, you have to add the displacement with your starting address of the segment or block, and then you will get your effective address. Are you following what I'm saying?
Doctor, I just don't understand the displacement part. What do you mean by adding?
Displacement. Okay, displacement part basically what we can say, usually in the memory, we can make a segment. Says this is your one segment. This is your one segment. This is your another segment. So, this is your another segment. Now, what happens usually in order to access to a particular memory location, we need that. This is our beginning of the segment. Say 0, 0, 0, then 0, 0, 0, then 0, 0, 0, then say 2, 5, 3, 8. So 25EA is the beginning of one segment. Same way 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, then say 3000. Okay, so it is not easier if we put 2000. So the starting address of this block is 2000. But if you want to access a particular bytes within this block, then first byte you can access by adding 0 to 8, which is the if you add 2000 plus 0, so that is this memory location. Second byte, if you want to access 2000 plus 1, that will give you the access to this memory location. If you want to access the fifth byte, then you have to add 2000 plus 5. This 5 is your displacement, because 2000 is the beginning of your block, And if you want to go here, that is 2000 plus 5, which is displacement, that will give you the address of this memory location. So usually we keep this address 2000, 3000, then say for example 4000. Sorry. And by using this starting address, we can access any particular byte within the block, within the segment. Say for example, one of the register is containing this starting address of the memory location, and in your instruction is basically containing the displacement. How far from the starting address of your block, how far is your memory location, which is containing your operand. Okay, so for example, if your operand is here, this is containing your data. Say data 45 is there, and so what we will say in our instruction, say we want to do a add instruction. Say for example, add instruction is 1101. This is our add instruction. Now one of your register is containing your destination register is 1101, and this register number 13 is basically your destination register where your result will be stored. And then we are saying that register number say 0100 is going to contain my base address. Base address means it will contain the address of the starting address of the segment, So register number 4 is going to contain the starting address of the segment, and this is 0101. This is basically displacement. So this is your whole instruction. You can see this is your opcode that is basically telling that you have to perform an add operation. This is basically telling this is your destination register, and this is telling that this is my one of the register that is containing your address. So you have to go to this register. You will find the address is this, but this address is not your effective address. With this address, you have to add this displacement, which is 5. That will tell that 4000 plus 5 is this one. The address is basically 4005. That is the address where is your operand. The operand is stored. Are you following?
Yes, it's clear.
Okay. Now, base register addressing, you can understand that the instruction does not contain the starting address of your memory location. Rather, instruction contains the register number that contains the starting address of the memory location, but instruction also contains the displacement. So in order to get the effective address of a memory location, you have to first go and access your register, get the starting address of the memory location, and with that you have to add the displacement which is in your instruction, add that to your base address. That will give you the effective address. So that's base register addressing, but you have another type of addressing which is called indexing. Indexing is completely opposite to your base address register. In case of indexing, what will happen? The reference register contains a positive displacement from that address. That means the address field references a main memory address. So your instruction, the instruction contains directly the address of the memory location, starting address of your memory location, but the displacement is not stored in the instruction. Rather, displacement is stored in one of the register. So one of the register basically contains your displacement in case of indexing addressing, but your starting address is stored in your instruction itself. Are you understanding what I'm saying? Or are you understanding the difference between them?
Yes.
You're the only student who is answering it?
Yes, Doctor.
So try to understand the difference between these two. In both cases, that in order to get an effective address, you need to know the starting address of a segment, and you have to also know the displacement, the distance from where, from the beginning, how far you have to go so that you can get your actual memory location that is containing your operand. So in case of base register addressing, what we do in the instruction itself, it contains the number of the register, where register contains the starting address of your memory location, and the instruction itself contains your displacement. So through the register you have to get the starting address, and from the instruction itself you get the displacement. You have to add them together, you will get the final result. You will get the effective address of your operand. In case of indexing addressing, what happens? Your displacement is stored in one of the register, but the starting address of your memory location, that is any particular segment, the starting address of any particular segment is stored in the instruction itself. Instruction itself contains the starting address. But displacement is stored in one of the registers, so you specify the register number to get the displacement. So in this indexing will use when you use the array, but base register addressing are used when you use accessing single element of the array, but indexings are used when you are accessing all elements of the array in a sequence, in a loop. So we use the indexing addressing. So that's the basic idea. Let's try to solve our class assignment. Is it all right? Can we solve the class assignment, or you want to stop now?
I don't know. It's okay for me.
Yes, let's.
Okay, some students saying stop.
Okay. Is it some students saying stop?
For me, it's okay. No.
What about the others?
No problem, Doctor.
No problem. Okay. So let's solve our class assignment number 5. So first question: assume that a hypothetical processor use the following instruction format, only 16-bit instruction format, for register indirect addressing mode. You know that register indirect addressing mode, register contains the address. Some register contains the address, and that address of the memory location contains your operand. So register does not contain your operand directly. Again, register indirect addressing. Usually what happens, register addressing, register contains your operand. Register contains your operand. So in your instruction, you specify the register number 5 contains my first source operand, register number 7 contains my second source operand. So you add them together and store the result in the destination register. So register number, basically register itself contains your operand. And in your instruction, we specify the register number. So in this case, this is a register indirect addressing. So register does not contain your operand. Rather, in the instruction, we specify the register number, and from the register, we'll get the starting address. Not starting, we will get the address of the memory location, and that address is containing your operand. Okay. So this is your instruction format. You can see that opcode is 5 bits. Your destination memory address register is 3 bits. First source register, source address register is 3 bits. Second source memory address register is also 3 bits, and your mode bits is 2 bits. Basically, the mode bits are used to specify which addressing mode you are using here. So these 2 bits basically tell that we are now using register indirect addressing mode. So some instruction itself to specify that which addressing mode we are using. Yes.
Doctor, can you zoom, please?
Oh, sure. Can you see it?
Yes.
Okay. Now you can see that our opcode is 5 bits. This is consider the following instruction written in register indirect addressing mode. In this instruction, you can see the first 5 bit is basically referring to our opcode. Then next 3 bits basically referring to our register, and that register is containing the address where our result will be stored. So register number 7. Have you seen that register number 7? This is register number 7. It's not it. This is the place where our data will be, our final result will be stored, or this register is containing some address where our final register is, final value is will be stored? Which one? Are you following what I'm saying?
Contain, Doctor.
No,
Contain the address.
no, contain the address where your final result will be stored. So register number 7 does not contain your final result. Register number 7, which is this one, which is containing some address of the memory location, where that memory location will contain your final result. Are you understanding? This
Yes.
is register indirect addressing. That means register is not going to contain any operand or final result. Rather, register will contain always the address of the memory location, and that memory location will contain your either operand or final result. So in this case, this is register number 7, which is referring to this one, that referring to a memory location 5FED, and this memory location, you see that this memory location is 16-bit memory location, but we cannot refer 16-bit here. We are referring only 3 bits, and referring 3 bits means we can refer to only register, only 8 register. So referring 111 means register number 7. This is register number 7, and register number 7 is referring to a memory location. So this is the memory location where your final value will be stored. But this is your first source address register, which is register number 5. So is it register number 5 is containing your first operand?
I guess it's containing an address also.
Yes, 101 register number 5 is not containing your operand. This is not your operand. This register number 5 is containing the address of the memory location that is containing your operand. The same way, this is 010. This is register number second source memory address register, 3 bits. So register number 2. So register number 2 is containing some memory location, and this memory location is containing your second source operand, second operand. Okay. Now answer the following question: what is the address of the destination memory location? Address of the destination memory location. In which memory location your final result will be stored? Tell me. Quick.
R7.
R7 is containing the memory location. I'm asking you, what is the address of the destination memory location? Which memory location your final result will be stored?
5FED.
5FED. That is the memory location where your final result will be stored. In your instruction, it is referring to R7, which is the register, but register is not going to contain your final result. Rather, register containing some address, that address will contain your final result. Are you understanding? Everyone. So that's your result.
Yes, Doctor, but
Answer for the first.
but it's 16 bits, Doctor.
Yes. So what's the problem?
The destination register is only 7 bits, 3 bits.
Yeah. So
This is the register number.
destination register number only 3 bits. So that's why we are using 3 bits to refer to one of these 8 register. One of these 8 register you need only 3 bits. That's fine. But the registers are not containing your operand. Registers are containing your address of the memory location, and the memory location is containing your operand. And in your instruction, you are not referring to this address. You are referring to this register, and register is referring to your memory location where your final result is stored. Are you understanding? Are you
Yes.
understanding? What is the address of the first source memory location? What is the address of the first source memory location? What is your first operand? In which?
189C.
So basically, your first source address register is register number 101. 101 is register number 5. And register number 5 is containing memory location 189C, and this is the memory location where is your first data, first operand is stored. So this is 189C. 189C is the address of the memory location where your first operand is stored. What is the maximum memory location the instruction can address? Tell me.
FF.
Fantastic. Because our maximum address is 16-bit, because you can see that each registers are 16-bit and each registers are containing 16 bits address. So our maximum memory location that can be referenced is FFFF. So this is the address of the memory location that can be referenced. Remember, 2 to the power 16 will give you 32,768, and that is the maximum memory location that you can refer using register indirect addressing mode. Now let's see this one. Assume that a hypothetical.
Is it okay if we put 2 to the power 16?
2 to the power 16 is basically telling that how many bytes can be accessed using register indirect addressing. How many bytes? Okay, so 2 to the power 16 will basically tell you how many bytes you can access using register indirect accessing. 72,768. That is the number of bytes, because 2 to the power 16 is that. Just check. 2 to the power 16 is 65,536. Sorry. 65,536. This number of bytes can be accessed in register addressing mode. But what is the maximum memory location? The lowest memory location is 0000, because that's the 16-bit, and the highest memory location, maximum memory location, is FFFF. So this is, if I ask you what is the or how many memory bytes can be accessed using register indirect addressing mode in this particular case, that is the answer. But what is the maximum memory location the instruction can address? The maximum memory location the instruction can address is FFFF. Are you understanding? Is it clear?
Yes, Doctor, it's clear.
Okay, first I will use the question number 3 because this one I have already done with you in the preparation in your midterm exam, I think. Assume that a hypothetical processor uses the following instruction format: 24 bits for immediate addressing mode. This is very simple one. So what is the instruction size? 24 bits. Opcode, we can use 6 bits for the opcode. Destination register, only 4 bits. Source register, only 4 bits. Immediate value, maximum is 10 bits. Now answer this question. How many opcodes the processor can have? Tell me. Answer. How many opcodes the processor can have?
64.
2 to the power 6.
64. 2 to the power 6. Yes, 2 to the power 6, because for opcode we have total 6 bits. Since we have total 6 bits, 2 to the power 6 is basically 64 different opcodes. Okay, so this hypothetical processor can have maximum 64 different operations or 64 different opcodes. So this is the first answer. How many registers the processor can have to be addressed using 3 bits? So here actually we are not using 3 bits, we are using 4 bits. Can you change it to 4 bits? Can you change it to 4 bits, please? So using 4 bits, how many register, either destination or source register, you can reference? How many registers? Tell me.
16.
Because you can see destination registers we are using 4 bits, source register we are using 4 bits. My question is that using 4 bits, how many register you can reference to?
2 to the power 8, I guess.
2 to the power 8. How did you get 8?
Because we have 2 4 bits register.
Please. One is these 4 bits for destination register. These 4 bits is source register. I'm asking you how many registers the processor can have to be addressed using 4 bits. If for destination register, how many registers you can have?
2 to the power 4, 16.
That's 16. That's the answer.
Yes.
2 to the power 4. That is 16 different register. It can reference to use for destination register, or to the power 16. It can reference to for source register. So to the power 4 is 16. What is the maximum immediate value that can be used in the instruction? What is the maximum immediate value? Have you seen that immediate value? How many bits we can
Yes.
use for the immediate value?
2 to the power 10.
So what is 2 to the power 10? So if we use 2 to the power 10, can anyone tell me what is the value of 2 to the power 10?
One thousand.
1024.
1024 if the number is unsigned number. But if you want to store signed number, then it will be 2 to the power 10 minus 1. Are you understanding? If it is a signed number, then it can be maximum to the power 9 to the power 10 minus 1 minus 1. Why? Because when it's a signed number, you have to use 1 bit for the sign, is not it? So this is the formula that I have shown you in case of 2's complement representation. So in that case, basically you can you can use minus 512 to plus 511. These are the signed number that you can use. Maximum signed number you can use. If it is an unsigned number, maximum value from 0 to 1024. But if it is a unsigned number as the immediate value you want to use, then maximum value, unsigned value is minus 512 to plus 511. That's the maximum value you can use. Is it all right, everyone?
Yes.
Yes.
Okay, now assume that a hypothetical Okay. Now, assume that a hypothetical processor uses the following instruction format 32 bits for the base register addressing mode, where the second source operand is stored in memory. Second source operand is stored in memory. The address of the second source operand is calculated based on the memory address and the displacement. Are you understanding? So in this instruction format, you can see that you have total 32 bits. 4 bits you can use for the only opcodes. Destination registers you can use using 4 bits. First source register you can use using 4 bits. But second source register address you can use 16 bits. Displacement is 4 bits. Calculate based on the memory address and the but this is not a base register addressing, this is an index register addressing. Index addressing, indexing. Can you remember in case of indexing? What happens in case of indexing? Address field references a memory location, address of the memory location, and the reference register contains a positive displacement. So register basically contains the positive displacement. So displacement is 4 bits. I think there is a mistake in this code, but if I take this register displacement, because in our base register addressing, we have a register contains the memory location address. Okay. It's a base restart pressing, I think. Base restart. Here, source memory address. No, I think we need to fix. I need to fix this question. It cannot be 32 bits. Leave it as it is. I will fix this question and I will discuss it in the class. Okay. This question is not right. I need to fix this question. Okay.
Okay.
Okay, thank you.
Thank you because we are already finished our time. So later on, I will fix this one and I will discuss this one. But we need to solve two problems related with base addressing and indexing, because you might get one question from base addressing or indexing. So I will solve at least one problem using base addressing or indexing in the class, inshallah. Okay. So you just submit me in these two problems, solution of these two problems. Okay.
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 So see you inshallah tomorrow.
Thank you very much, doctor.
Thank you.
Have a good night.
Assalamu alaikum.